The recent spectroscopic observations of the interstellar object 3I/Atlas, particularly through the advanced capabilities of the Atacama Large Millimeter/Submillimeter Array ALMA, have provided groundbreaking insights into the complex chemistry of this distant visitor. The detection of methanol, CH3OH, and hydrogen cyanide, HCN, marks a significant milestone in our understanding of the chemical composition of interstellar objects and their potential connection to the origins of life. These molecules are not only commonly found in the cold interstellar medium, but also play a crucial role as precursors in the complex organic chemistry that may underpin the development of life as we know it. The identification of such molecules on 3I/Atlas raises important questions about the possibility of panspermia, the theory that life, or at least the basic building blocks of life, may be transported across the cosmos through the movement of interstellar objects. The detection of methanol near 3I/Atlas during various observations in 2025, on August 28, September 18, and 22, and October 1, as well as the presence of hydrogen cyanide on September 12 and 15, provides a fascinating glimpse into the chemical processes occurring in distant regions of space. The distances of 3I/Atlas from the Sun during these observations range from 2.6 to 1.7 Australian dollars astronomical units, a range that places the object in a position where it is still relatively far from the Sun, yet close enough for its chemical activity to be observed in detail. The observed production of hydrogen cyanide was found to be lower in the sunward direction, which is a notable feature. This depletion suggests that the production mechanism of hydrogen cyanide on 3I/Atlas is intimately linked to the nucleus of the object, whereas methanol exhibited an enhanced production in the sunward direction, indicating that methanol might have been formed in a gaseous plume emanating from the object itself. This differentiation between the production of methanol and hydrogen cyanide offers valuable insights into the chemical composition of the object and its evolutionary processes as it travels through space. The increase in methanol production observed from August to October 2025 reveals an intriguing pattern. The production rate followed a power law dependence on heliocentric distance, with a power index of -5.2 plus or -0.6. This finding suggests that the chemical processes occurring on 3I/Atlas are not static, but change dynamically with the object's position relative to the Sun. The increase in methanol production over time could be indicative of a variety of processes, including sublimation or other chemical reactions occurring in response to the increasing solar radiation as 3I/Atlas approached the inner solar system. The presence of methanol in significant quantities on an interstellar object is noteworthy because it is a fundamental molecule in organic chemistry and could have far-reaching implications for understanding the potential for life elsewhere in the universe. Methanol itself is an abundant molecule in star-forming regions. Its discovery in such regions, including its detection by the Merlin Array in 2006 and by ALMA in 2016 around the young star TW Hydri, highlights the ubiquity of methanol in the cosmos. Methanol is a crucial building block for more complex organic molecules, including amino acids and sugars, such as ribose, a key component of RNA and DNA. These molecules are essential for the biochemistry of life as we understand it, and their presence in the interstellar medium, as well as in comets and other celestial objects, raises the intriguing possibility that interstellar material may serve as a conduit for the building blocks of life across vast distances. This idea, known as panspermia, posits that life or the precursors to life could be transported from one planetary system to another, potentially allowing for the widespread distribution of organic compounds necessary for life throughout the galaxy. In addition to being a building block for complex molecules, methanol plays an important role in terrestrial life. Certain microorganisms, including bacteria and yeasts known as methylotrophs, can utilize methanol as their sole source of energy. These organisms possess specialized enzymes, such as methanol dehydrogenase, which allow them to oxidize methanol to formaldehyde. This formaldehyde can then be assimilated into biomass or used to produce valuable compounds, such as amino acids. Methanol is also produced naturally by plants, where it primarily results from the breakdown of cell wall components like pectin. In plants, methanol acts not only as a byproduct, but also as a signaling molecule, triggering defense responses when the plant is wounded and helping regulate immunity against pathogens. This dual role of methanol, both as a precursor for life's building blocks and as a participant in metabolic and defense processes, highlights its biological significance. On the other hand, hydrogen cyanide, though toxic in high concentrations, also plays an important biological role, especially in signaling. This molecule has been measured in the atmosphere of Titan, Saturn's largest moon, by multiple space missions, including the Cassini probe. Hydrogen cyanide has a dual nature. While it can be highly poisonous at high concentrations, it also serves as an important signaling molecule at lower concentrations in plants, animals, and microorganisms. The chemical properties of hydrogen cyanide allow it to act as a precursor for a wide variety of complex organic molecules, including amino acids and nucleic acid bases, such as adenine. This capability places hydrogen cyanide at the heart of the biochemical pathways that form the basis of life. Moreover, some bacteria produce hydrogen cyanide as a secondary metabolite to inhibit the growth of competing microorganisms. By disrupting the respiration of other microbes, hydrogen cyanide can serve as a chemical defense, allowing certain bacteria to outcompete others in their ecological niche. In plants, hydrogen cyanide is produced as a byproduct of the breakdown of cyanogenic glycosides and as part of the ethylene biosynthesis pathway. At low concentrations, hydrogen cyanide can promote seed germination and enhance resistance to environmental stressors, such as salt, cold, or pathogen attacks. Its presence in plants as a natural defense molecule further emphasizes its role in maintaining ecological balance. At higher concentrations, however, hydrogen cyanide acts as a potent chemical weapon, deterring herbivores and pathogens from damaging the plant. In mammals, hydrogen cyanide's biological activity extends to the nervous system, where it can activate specific receptors, influencing signal transduction pathways, and even contributing to opioid-induced pain relief. These diverse roles of hydrogen cyanide, from defense to regulation, underscore its importance in living systems, despite its toxicity. The discovery of both methanol and hydrogen cyanide on 3I/Atlas prompts further speculation about the nature of this interstellar object. Is it simply a benign traveler through space, carrying with it the potential building blocks of life, or could it pose a threat by spreading toxic substances across the solar system? The anomalously large ratio of methanol to hydrogen cyanide production on 3I/Atlas leans towards a more favorable interpretation. The fact that methanol, a precursor to key biological molecules, is more abundant than hydrogen cyanide, which can be toxic at high concentrations, suggests that 3I/Atlas could be a friendly interstellar visitor. Its composition points more towards the possibility of panspermia, the idea that interstellar objects may serve as vectors for the spread of organic compounds that could seed life on planets like Earth. The presence of methanol and hydrogen cyanide in such ratios on 3I/Atlas is reminiscent of the composition of comets, which have long been suspected to play a role in delivering organic molecules to planets. Furthermore, the detection of these molecules in the cold, distant reaches of space suggests that complex organic chemistry is not limited to our planet or even our solar system. If interstellar objects like 3I/Atlas are carrying significant amounts of organic material, this opens up new possibilities for the widespread distribution of life's building blocks across the galaxy. This idea adds weight to the notion that life could be more common throughout the universe than previously thought, with interstellar objects acting as conduits for organic compounds that could jumpstart life wherever they may land. In conclusion, the spectroscopic observations of 3I/Atlas and the detection of methanol and hydrogen cyanide provide a unique